Most lectures on logistic regression follow the same pattern. They start with a line, then introduce this curve and say it turns scores into probabilities. And while that's true, it skips the part that actually makes it make sense. Where does this curve come from? Instead of starting with formulas and definitions, we'll start with a simple idea and follow the breadcrumb trail of where it falls short. We'll refine the idea step by step so that nothing feels randomly introduced, and complex ideas like this curve don't just appear, they emerge as the natural path forward. This is how I think about logistic regression. In an attempt to improve exam pass rates, a school decides to survey its students. For each student, the school records the length of the exam they took, the amount of time they studied for it, and whether they passed the exam. This student studied 3 hours for a 2-hour exam and passed. This student studied 2 hours for a 3-hour exam and failed. As they get more data, the school notices a pattern. Students that passed the exam studied more relative to the exam's length than students that failed. In order to help a student succeed, the school needs to understand exactly how much more a student needs to study in order to pass their exam. They're looking for the exact tipping point between passing and failing. Just through visual inspection, the threshold between passing and failing would be somewhere here. All students to the right of the line passed, and all students to the left failed. This threshold, however, is just an educated guess. Notice that these other lines could also arguably be the tipping point between passing and failing. More data might allow some refining, or make the task much more challenging, but we'll get to that. If we look at all students who studied 3 hours, since they each had different exam lengths, 3 hours was only enough study time for some of them. I like to think of this line as the bare minimum amount of work required to pass. The bare minimum depends on both study time and exam length. Since students seem to have to study at least as much as the exam is long in order to pass, maybe the bare minimum is when study time exactly matches the exam length. A student that studied 3 hours for a 3-hour exam would be on this line, for example. But notice that we can subtract exam length on both sides of the equation and rewrite it as study time minus exam length equals 0. Although you may be less familiar with the equation of the line in this form, it's a crucial step to unlocking the secrets of logistic regression. Study time minus exam length measures exactly how much more work the student did compared to the bare minimum. A work of 0 means they did the minimum. It doesn't matter if we're talking about a student who had a 1-hour exam or a 4-hour exam. If both put in a work of 0, it means they studied exactly as much as their exam is long. The more work they do, the farther to the right of the threshold the student lies. The less work they do, the farther to the left the student lies. Theoretically then, the school can help students succeed by encouraging students to put in the minimum amount of work. But that's not very realistic. Doing the bare minimum rarely guarantees success. What's more, students learn at different rates, and some may study an hour more than the exam and fail, while others study an hour less and pass. The greater the study time relative to the exam length, the more students we expect to pass. Similarly, the less they study, the less we would expect the student to pass. So the threshold now isn't exactly a tipping point, but a zone of total uncertainty. If a student did the bare minimum work, whether they pass would be like flipping a coin. As student work increases from an hour more than the minimum to 2 hours more to 3 hours, we notice a bigger and bigger fraction of students pass the farther from the threshold we are, going from 60% to 75% to 100%. But what if we now encounter a student between 60% and 75%? Intuitively, we understand that their probability of passing should be somewhere in between 60 and 75. But what exactly? Consider two students. Student A studied an hour more than the exam's length, and student B 4 hours. Naturally, we might argue that since B put in 4 times the amount of work than A, it should be 4 times more likely for them to pass compared to A. So, one thing we can do is assign probabilities corresponding to the relative work students did. Since student A put in 1 unit of work and student B 4 units, Relatively speaking, out of a total of 5 units of work, A did 20% and B did 80%, which aligns nicely with our intuition that the probability of B passing should be 4 times that of A. What we just did is called normalization. We adjusted the work relative to the total in order to get a relative contribution. That relative contribution sums up to 1, just like a probability. But there's a slight issue. This doesn't work for negative numbers. If student A studied an hour less than the exam's length, their work is now negative. And if we repeat the process, we would end up with negative 1/3 and 4/3, both values outside the range of probabilities. I know what you're thinking. Why not just take the absolute value of -1? Well, if we take the absolute value, then -1 behaves like 1, and the odds of passing relative to 4 would be the same. But that shouldn't be the case. A student who studied an hour less than the exam's length put in way less work than a student who studied an hour more. But the idea is great. We do need a way to convert negative work into positive numbers. We just need to do it in a way that preserves differences in work so that -1 isn't confused for the same amount of work as 1. But how? Consider that the more negative the work, the less effort that student put in. What we'd like to do is to convert work, which can be both positive and negative, into a measure of effort that is never negative. Effort should decrease with the amount of work, but never become negative. Let's say for a work of 0, the function returns an effort of 1. That means that all negative work needs to be converted to efforts between 0 and 1. If we reduce work by 1 by taking a step of size 1, how much should the effort decrease? It cannot decrease by 1, otherwise we would be at 0 and there would be no room left for all the other negative numbers. So let's say we decrease by 1/2 instead. If we take another step from -1 to -2 now, we cannot again decrease by 1/2, otherwise again there's no room for the other negative numbers. So maybe we can shrink the output by halving it again, and so on. Every step, we shrink the output by halving the previous output. That way, effort will never be 0. Every time we get close, we'll only take a half step towards 0. To keep the process consistent, that means positive work will get mapped to a compounded value of effort. Such a function is called an exponential function. It's a function whose rate of growth defies intuition. There's a famous riddle about a bacteria that doubles every day in a jar. Today, after 1,000 days, the jar is full. When was the jar half full? Intuition would have us guess somewhere in the range of day 500, but because it doubles every day, it was half full yesterday. In practice, we use the exponential function, not just any exponential function. You can think of it as E for effort. It has a special property that we'll get to later, but realistically, you could translate any exponential function into the exponential function using the following formula, which basically equates to scaling the data, either stretching or compressing it. Now we have a way to convert student work into effort. We can now create probabilities as the relative difference in effort between two students. We first get the work they did by looking at the difference between their study time and exam length, then convert that work into effort using the exponential function. Finally, we use normalization to calculate the relative share of the effort as probabilities. But recall that our intuition demanded that students close to the boundary get assigned a probability close to 50-50 because this is the zone of uncertainty. That threshold represents the bare minimum amount of work required so that your chance of passing the exam is higher than failing it. But probability seems to depend on which student we're comparing against. So can we find a unifying point of comparison? Consider that the difference between study time and exam length, capturing the amount of work a student put in, is already comparing itself implicitly. It's basically how much more work the student did compared to the bare minimum. So instead of building probabilities by comparing two students, let's compare students against a hypothetical student who is on the threshold and studied exactly the exam's length. To get the probability student A will pass, we calculate the work they did by taking the difference between study time and exam length, then convert it to effort using the exponential function, And finally, create a probability as how much more effort they put in compared to the bare minimum. Put those steps together, and the entire process becomes a single function. That function is called the sigmoid function. The sigmoid function is a special case of a family of functions called logistic functions, hence the name logistic regression. Given a difference between study time and exam length, we can find the probability the student will pass the exam using the sigmoid function. For example, for a difference of 6 hours, the probability is close to 100%. For a deficit of 6 hours, the probability is close to 0. And for a student on the threshold where they studied exactly the same as the exam's length, their probability is 50%. I know what you're thinking. What's this other probability? Well, if the probability of A is the probability they pass the exam, the other probability will be the probability they fail the exam. Intuitively, because they express a relative share of effort, they must sum to 1, and thus the other probability is 1 minus the probability A passes. So one way to interpret it is as the probability of A failing the exam. What's interesting is that not only is this probability of failing 1 minus the probability of passing, it is also a sigmoid function, an exact mirror of the probability of passing. We started from a simple goal of finding what sets apart students that pass from those that fail exams. We found a threshold between passing and failing, a line representing a relationship between study time and exam length, which allowed us to measure how much work a student did, or didn't do. We tried to turn that work into a probability by comparing the relative work between two students. But negative numbers made that difficult, and simple fixes like taking the absolute value lost something important: which side of the threshold the student is on. So we needed a way to keep that information while making everything positive. This led us to the exponential, turning work into effort. Once we had that, probabilities came out naturally by comparing relative effort to the baseline, which is the sigmoid function and backbone of logistic regression. But there's still much more to this story. How do we find the right line? How does this extend beyond two groups? And importantly, how do we make sure these probabilities actually match the data we have? That's what we'll look at next. Like and subscribe for more content like this.